Okay, so I'm just going to do a very simple explanation here of how you can use this master work equation to solve many different things. So remember, our master work equation is dealing with the net work equaling the conservative plus the non-conservative. And I'm going to give you this situation. I have a block, a 10 kilogram block. It's on an inclined plane. It's a rough surface, somewhat rough. The mu is zero point 0.4. It's 20 meters long, and it's 10 meters high. And what I would like to do is find out what is the speed going to be when it reaches the bottom. Okay, so I'm going to say, what is the speed when that object reaches the bottom? Okay, and I want to solve this using energy. So that's what I want to do. So the first thing I want to do here is I just want to identify what forces are acting on this box. We know that it has a weight, right? mg. We know that it has a normal, right? We know there's going to be friction. Friction is going to oppose it like this. What we need to do, though, is we need to resolve this into its components. So I know that this is going to be force times the normal here. It's going to be force of friction. I'm going to have this force of gravity straight down here. Those are the forces. Those are the natural forces acting on this box. I did not draw friction acting at the surface, even though it does, just to keep this example simple, but I'm drawing friction applying at the center of mass, just to simplify the situation. Okay, so we know this is 10 kilograms. The next thing I want to do is I want to define an axis. What is the axis that I want to use? And so the basic way we answer that question is the following. This is how I do it. I want to know what is the direction of my net force. Where is it going to be? My net force is going to be in this direction. So I'm going to define that as my x direction going down the plane. So I'm just going to tilt my axis. And I always want to have my axis, my positive axis pointing in the direction of my net force. My net force is going to be going that way. But I have one force here that's not directly in that coordinate system. So I'm going to have to convert the components of that, and that's gravity. So let's take a look at that. Okay, so what I've done here is I've just drawn my components of gravity here. I made my frictional force a little shorter, the arrow, the way that I had it drawn before. It couldn't have accelerated down, but okay. So this component here has to be more. So let me just draw that in. So this, remember, f of g is going to be mg. Okay, so this is mg sine of theta. And theta is simply this theta here. And this is going to be mg cosine theta. And so now that I have my components, I know that in this y direction I have a static situation. I have the normal is going to equal mg cosine theta. And I know that friction equals mu times the normal. In other words, friction is going to be mu times mg cosine theta. So that's the frictional force. So why do we even care about that? Well, I'm going back here to this equation. I want to find the net work equals the conservative plus the non-conservative. I need to know what friction's doing because it's a non-conservative force. Okay, so I needed to know this just simple component here. And the only thing here we don't know is the theta, the cosine of theta. We can figure it out from this triangle. We know that this is going to be a 30, 60, 90 triangle. Just because I drew these, it's a similar triangle to a 30, 60, 90, right? So we know across from the 30 is smallest side, the hypotenuse is the largest, which is 2. So this is simply going to be 10 root 3 here. Okay, why is that important? Well, when we do the cosine, it's going to be important. Okay, so let's go back to our equation here. So I'm going to say the net work is the change of the kinetic, and the conservative is the negative change of potential, plus the work not conservative. In this case, it's going to be negative force of friction times the displacement down the ramp, okay? And the dot product. And the reason I took negative is simply that the displacement in this direction is 180 degrees from the force of friction. So that's negative. It's taking energy away from the system, that's for sure. Okay, so I'm going to write this out now. So here's my long equation. 1/2 mv final squared minus v initial squared equals negative mg delta h. minus force of friction times the distance down the ramp. Okay, so we know my initial speed is 0. It starts from rest, and I'm going to say what's the speed when it hits the bottom. And if this was just a simple energy question and we didn't have friction involved, we could have just quickly said, okay, 1/2 mgh is 1/2 mv squared, and the speed at the bottom, if there was no friction, right? If no friction, if we had a complete conversion of energy, if no friction, we know that the speed at the bottom is going to be the square root of 2gh. Okay, that's just a simple conversion. But there's friction. Okay, there's a non-conservative force, and the whole point was to show you how to use this equation to solve these. So we're going to have 1/2 mv squared equals negative mg delta h minus force of friction, which is what? Mu mg cosine theta times d. Notice here that all of my masses will go bye-bye. Okay. And I can multiply over now my 2, so I can end up with this. So finally, after we go ahead and we cancel out the masses, okay, and we solve for v, we basically see that v is going to be negative 2g times, parentheses, we factored out a 2 and a g, okay, delta h minus mu cosine theta d. And the cosine of theta, don't forget, if this is a 30, 60, 90, is just root 3. Cosine 30 is root 3 over 2. Okay, so we can plug that in. But that's the speed when it hits the bottom. Symbolically, did it both ways, just to show you how this net work equation, master work equation, works. And don't worry about this negative in here, because my delta H, remember, is negative, right? So it's negative 10, right? So that's gonna give me a positive term, and then this term just represents the frictional term, taking away from the speed. In other words, it's detracting from the speed. So let's go ahead and actually find out what the speed is at the bottom. Okay, so let's calculate what that speed was. There's one little sign issue here. When I factored out this negative 2g, this should be a positive here. But aside from that, everything else looks good. So what's the speed when it hits the bottom? Let's do that calculation. Well, the one thing we should do first is we should ask ourselves, well, what would the speed be if there was no friction? Because we're going to use that as a test, okay? So we're going to see v equals the square root of 2gh. That would be, what would the speed be if there was no friction? So 2 times 9.8 times 10. That would be the speed with no friction. And in that case, that turns out to be 14 meters per second. Okay, so that's important because we need to know what would the speed be without friction, and if our answer should be less than that. I mean, that's, if we're doing this correctly, the answer should be less than 14. So let's find out what that answer is. So when we multiply all that out, we get 7.76 meters per second, something like that. Okay, so again, that's reasonable, right? We wanted it to be less than 14, and it was, so there you go. So that's just an example of using our master work equation here. Make sure you get the signs right, obviously at the end, to find out what the final speed would be if we had a non-conservative force going on there. And we could have added other things in there. I mean, we could have had, like, a spring pulling it to the bottom, or the engine of a car. We could have had another non-conservative force. But no matter what you do, you can always go back to this master equation to find out what the answer is.